Okay, thank you very much. So this has been work that I've been doing as a Survey NASA postdoctoral fellow, physically located at Surrey in Boulder. And so the general question here is understanding, what does the distribution of things in the asteroid belt tell us? And specifically, what interests me the most is what is it telling us about the process of planet formation? So we've known for a long time that the asteroid belt is in general composed of two different types of material. There's the bright, volatile, poor, kind of S-complex asteroids, which were originally thought to be mostly in the inner region of the asteroid belt, and the C-complex, darker, volatile, rich asteroids that were originally thought to mostly be in the outer part of the asteroid belt. And this led to a nice picture that we had this gradient in volatility that corresponded with this nice gradient in condensation sequences in the early protoplanetary disk, and everything makes sense. Except for when people started looking in more detail, it became clear that these two populations actually are very, very mixed. There's a broad overlap in regions populated by the more refractory and the more volatile rich asteroids. Even more, as meteoriticists start trying to understand in detail what's going on in these different populations, we see that not only are they overlapping in space, but they are very chemically distinct, both isotopically and in the elemental abundances. So how did you get these two populations, which are so different, but yet seem to be occupying approximately the same regions in the solar system? Furthermore, when Dawn went by Ceres, it saw that there are these ammoniated phyllosilicates on the surface of Ceres. So these are now compounds which are even thought to represent very distant regions of the solar nebula, but somehow this material ended up, smack dab in the middle of the asteroid belt in the inner solar system. So how can we explain this? Well, the asteroids have been spending all of their evolution pretty much doing whatever the large planets in our solar system have been doing. All of the structure that you see here is pretty much due to resonances with the giant planets in our solar system. So in order to understand the asteroid belt, we first need to take a step back and think about the giant planets in our solar system. So in order to form a giant planet, you first need to form a icy, rocky core of around 10 Earth masses inside the early gas-rich protosolar nebula. It turns out that it's actually kind of hard to get a large enough, maybe 10 Earth mass rocky, icy core before the gas disk goes away. If you start out with the general idea was that you would start out with a bunch of planetesimals, so a bunch of asteroid-sized objects. If they're big, then as your core begins to grow, it gets a little bit bigger, and then it's able to scatter these planetesimals more efficiently. So you end up scattering away all of the food you're trying to eat. So this means that the embryos will quench their own growth, and you can't get a giant planet core. Previously it was thought, hey, maybe instead of using, more typical, 100-kilometer-sized asteroids, we can make our giant planet cores out of small, kilometer-sized ones. We know that there's gas in these disks, so if there's gas, that should be damping out the eccentricities of the asteroids you're trying to accrete, so maybe you can grow a little bit faster. But unfortunately, it was shown that you don't actually efficiently accrete these small planetesimals, these small asteroids. You just open up a gap in the planetesimal disk. So it turns out that accreting planetesimals is a horrible way to make the cores of the giant planets. Fortunately, a few years ago, there was a realization that pebbles are potentially the way to go. Now, when I say pebbles, I am not a geologist, so I do not mean the geological definition of pebbles. I mean objects which are small, so they may be millimeters, centimeters, even decimeters in size. But what's important is that they interact with the gas disk in a very specific way. So normally, an object going around is just feeling the sun's gravity, and so it's going to go around on Keplerian orbits. If you're a pebble, you are large enough that you still know you're supposed to be following this Keplerian orbit, but you feel enough gas drag to modify your orbit a little bit, and it causes you to spiral inwards towards the sun. And particularly if you fly by a large planetesimal, then you'll feel the gas drag as you fly by. So if you wouldn't mind starting the movie on there. So first we see what happens if a planetesimal flies by, and it just gets deflected and continues on its merry way. If a pebble flies by, on the other hand, it loses energy, and so it's captured and spirals inwards and is accreted by your growing planetesimal. So now we finally have a dynamically self-consistent way to form the cores of our giant planets. So what we've done is we've used LIPAD, which is the Lagrangian integrator for planetary accretion and dynamics. It's basically an n-body integrator combined with statistical treatment of small bodies so that we can trace planet formation starting all the way from pebbles and planetesimals all the way up towards mature planetary systems. So in this figure, in this movie, in a moment, we're going to be seeing how pebbles are going to be drifting inwards. They will be accreted onto our giant planet embryos, and we've placed a population to represent the surrounding planetesimals, so the surrounding asteroids, and we can see what happens as we start forming our giant planets. So the pebbles are in gray. You'll see them on the bottom. Okay, thank you. So as you see, the pebbles are coming in, our planets are growing, everything's getting scattered around, and we end up with our nice giant planets. But you also hopefully noticed during that the asteroids that were color-coded by their initial location in the disk have gotten scattered all over the place. And in the inner region here, there's now a mixture of populations. So here's a movie that's a little bit slower with one of the asteroids marked out here, if you could show that. So you can see the nice tisserand tails form, the asteroid scatters out, sampling a large region of space, but then at one point, when it's interior to Jupiter, it's actually the gas drag which decouples the asteroid from Jupiter and allows it to be implanted into the asteroid belt, where it will remain. So we can look at the bodies which are thrown into the asteroid belt, and if we then place Jupiter and Saturn in their current locations, it can sculpt the asteroid belt to show a population which generally looks fairly similar to what we see for the C-type asteroids. So we can end up broadly reproducing what we see without anything fancy going on in the formation of Jupiter-Saturn other than the fact that they just grew. Furthermore, we can take a look at where did the objects come from. And one of the interesting things is actually turns out that that big peak that originally was there in the kind of outer part of the asteroid belt, which then was destabilized and later on and was lost, was formed of a lot of the asteroids that were the closest to Jupiter originally. So because when Jupiter was small, it could scatter things a little ways, it moved things just on the other side of its orbit into the asteroid belt, but then those objects were then destabilized and lost. So we actually don't see a lot of material in the final simulations representing right near the Jupiter system and it's dominated by material that was a bit farther out in the regions where Saturn and the other giant planets were forming. And we're populating out to the whole regions where the giant planets were forming. So that's cool. We can make things from a large population in the outer solar system and implant them into the asteroid belt at reasonably high efficiencies. But one question is, Ceres. So we specifically brought up Ceres as being an object that we know has this signature of very distant solar system chemistry. So does this just mean that Ceres was one of those objects that formed out, at the outer regions of this disk and was just happened to have been transported in? Or does the fact that Ceres is the largest object and has the signature of outer solar system chemistry, is that important? So with pebble accretion, I showed you how as a pebble flies by an object, it can be efficiently accreted. It turns out that this process is very sensitive to the mass of your planetesimal. If it's low mass, it's very easy to fly by without being disturbed. So by the time that the pebble notices that there was a planetesimal there, it's already left the vicinity. While if you're a bit larger, the pebble is more disturbed and has a much higher probability of being captured. So in this figure here, we're seeing the size of an asteroid with the cumulative size distribution. The blue curve is going to be our model showing where planetesimals are being formed, and then the circles are indicating kind of the current distribution of asteroids, or well, the distribution of asteroids today. So if you could start the movie, then you see, so planetesimals are formed initially, and then pebbles are drifting inwards slowly over time. And the pebbles are preferentially being accreted by the larger asteroids. So it ends up going from a single power law initially, is then flattened out to create the size distribution we see today. So it's very possible that Ceres contains a significant amount of pebbles which have drifted from the outer solar system, from the very distant regions of the outer solar system, and were then accreted by Ceres wherever it formed within the kind of giant planet forming region before it was transported into the asteroid belt. We don't know that for sure, but it's one of the options available. So I will just leave that here. So pebble accretion is exciting because it's a fully dynamically self-consistent way of forming the giant planets. And it allows us to really be testing these ideas about how giant planet formation may have been affecting the asteroid belt for the first time. Thanks.
All right, thank you, Katherine. We have time for a question.
Oh, there we go. So this looks different than a lot of the Kepler observed solar systems. So what does that imply about the distribution of maybe pebble sizes in these initial proto-disks?
Yeah, so I think that the solar system is definitely weird. We have a giant planet and we don't have super Earths. So I think one possible explanation is that because we had a system where we were able to form a giant planet, once Jupiter forms, it will decouple the pebble flow from the outer solar system into the inner solar system. So pebbles can't get past Jupiter. So if we didn't have a Jupiter, then the terrestrial planets would expect to experience this, 20, 30, Earth masses of pebbles from the outer solar system should be drifting all the way into the inner solar system, potentially making like short period, super Earth type planets. So I think that so I haven't looked at this in detail, but I think that probably the growth of Jupiter whatever allowed us to make that first stage would be the difference between our solar system and the majority of solar systems we're seeing.
Are we set?
Thank you. We're
Oh,
going to
okay.
move up. We have more questions.